Hi, my name's Dylan, and today I'll be talking about what radar is and how it works.
So what is radar? Radar stands for radio detection and range. It was discovered back in the 1800s, but didn't come out until about World War II.
Okay, whenever you're ready, dude.
Okay, before we dive into exactly how a radar works, we need to talk about the fundamental particles and electromagnetic radiation that is emitted from certain electromagnetic processes. Visible light is one form, X-rays, radio waves, these are all types of electromagnetic radiation. Electromagnetic radiation is consisting of electromagnetic waves, and these waves are basically electric and magnetic fields that are moving at the speed of light, that oscillate at the same time and the same magnitude. Alright, so an electromagnetic wave is formed from a charged particle accelerating, just like Joey's about to show us. There he goes. Oh yeah. Electric magnetic waves kind of work like this piece of string here. They oscillate back and forth in a wave pattern. They are formed from electric and magnetic fields that move at the speed of light. If we stop right here, we can see the two peaks of these waves. That distance between the two is going to be your wavelength. And on the electromagnetic spectrum, which is all the different waves of electromagnetism, each category has different frequency and wavelength. Frequency is the amount of times that a wave hits a certain point in a given time, like 1 second, and this is measured in hertz. And while one wave is oscillating in like one plane, so we'll call that the magnetic field would be oscillating in one plane, the electric field would be oscillating perpendicular to that, exactly 90 degrees at the exact same time.
So as you can see on this chart right here, radio waves are going to be the longest wavelength out of the electromagnetic spectrum. Visible light, which humans can see, is actually a really small portion of the frequencies and wavelengths of these waves. So it's kind of interesting. We can only see a fraction of what is really out there. And for radar, like I said, radio is the wave that they use to detect objects out there. We'll get into that in just a moment. Okay, so you know how when you're in a valley or a big room and you make a noise and you can hear a reflection of that noise come back at you, kind of at a weaker sound, which is called an echo. That's pretty much how a radar works. It's going to shoot out a radio wave at a certain frequency, and once it goes out into the airspace, it'll hit an object and come back at it. This phenomenon is going to show you where an object is relative to the radar dish. This picture right here in front of you is a radar dish. The antenna shoots the frequency or the radio wave into the dish, sends it out into the airspace, and waits for it to hit an object and come back at a much weaker strength than what was shot out of it.
Okay, so our national airspace and air traffic controllers use Vortech, which is a very high frequency omnidirectional radar tactical air navigation. Basically, the higher the frequency of the radio wave, the smaller the object you can detect. If you have a very long wavelength, it's going to be really hard to see some of the smaller airplanes out there. So our national space defense systems will use the very high frequency and sometimes ultra high frequency just to detect missiles and faster moving objects. So when radar was first introduced, the issue was that they could only show where the object was relative to the radar dish. They didn't know how fast the object was moving, or they didn't really have a very good approximation of where the aircraft was in the sky. This issue was resolved when they discovered a phenomenon known as the Doppler effect. What the Doppler effect is, when wavelengths are traveling towards a certain object, when you are moving towards that object, the frequency is going to appear to be faster than what it really is. Where if the wavelength is moving away from the object, the frequency is going to seem a lot longer or deeper. It's going to be a lower frequency. Kind of like when you hear a siren going down the street. When the siren's coming at you, it sounds like the pitch is going to be a lot higher, because frequency is the determination of pitch and sound. So when it comes at you and the motion is towards you, the siren's going to sound a lot higher than when it is moving away from you. Once it starts to move away from you, it sounds a lot deeper in pitch or in tone. So when the wavelength is coming at you, it's going to appear like a higher frequency. When it goes away from you, it's going to appear like a lower frequency. What the Doppler effect was showing was that they could take this change in frequency from what the radar sent out to what the frequency is once it got back. So if the object's moving towards the radar, it would show a higher frequency, whereas if it was moving away from you, it would show a lower frequency. And they took the differences between these two frequencies to figure out how fast or how slow an object was moving either away from them. This is the same thing that police officers use in their radar guns to see how fast you're going, or if you're going up to a red light camera and it's trying to determine how fast an object's going. It uses the same principles, the same type of radar. And that's what radar is.